So, hi everyone. Before we begin, let's give a minute or two if there are some people still joining. I can see that the system is trying to let in another person, and here we go. The person was added. So let's give a minute or two, and maybe more people will join. If not, then we will just start. So now that everyone is here, and I will add anyone, while we are doing this meetup, I will add anybody in the waiting room. And now that everyone is here, we can start the second Pi Lithuania online meetup this year. And before we delve into our today's topics, I want to say a big thank you to our sponsors, Oxylabs. Their support is essential for us to bringing this community together. Without them, we would not be able to do these meetups. So again, just a huge thank you. And let's jump into today's agenda. And for today, we have two speakers, one presentation and one lightning talk. Petras Danavičius will do a presentation on how CPython remembers, a technical dive into CPython's memory management, consciously avoiding GIL and multi-threading. And we also have Albertas Agejevas, who will do a lightning talk on Python testing strategies and will share his nearly 20 years experience working with Python. And after each presentation, and we will have a 10-15 minute Q&A session where you will be able to ask questions in the chat, which we will read out loud, and the presenters will be able to answer them for you. So without any further ado, please welcome Petras for his presentation on how CPython remembers.
Okay, hello everyone. I will try to share my screen. Share screen. Stop. Can somebody tell me if everything is fine and you can see my screen and font size is okay-ish?
Yeah, we can see the screen.
How about you?
Yeah.
I'll try. Okay, let's say. Okay. So I think I can start. Okay, so hello, my name is Petras, and I will talk about how CPython saves stuff into memory, which should have been this talk's name probably instead of how CPython remembers. Also, I should have removed that C before Python, just how Python remembers. So why I added it? Because technically there's 4 Python implementations. So the most popular one is CPython. Then there's PyPy, there's IronPython and Jython. The problem is IronPython and Jython is that the latest version of those are 2.7. So they only support Python 2.7. And if I'm not mistaken, PyPy only supports Python 3.6 or so. So technically there's like 4 versions, but realistically there's only one. So CPython, VPython, and it's implemented in C. Right? So how it stores stuff into memory. So before that, a little bit about the talk. I'm not gonna talk about GIL or like multiprocessors. I'm gonna talk about very like small details, line by line details of memory management. So what's like the biggest problem with Python is that it's really slow. So we're gonna understand why from memory perspective. So what's a main rule of writing fast programs? It's picking up right data structures and correct algorithms. What's the problem with algorithms? I'm old and I cannot pronounce that in English correctly. That's why I'm not gonna talk about algorithms as well. I'm just gonna talk about memory management. So what's the like main rules of writing fast programs, like generic rules and memory management? There's like 3 important rules. First rule is to allocate memory to as less as possible times during program runtime. Also to free memory as less as possible. And the third rule is if CPU access some stuff, some variables together, like for example, in for each cycle, in for cycle, then those things I should lay in the memory nearby. So if you are like for eaching 1,000 of items, like 1,000 of integers, it would be great if all these integers are like nearby in one memory block. Why? Because memory usually is stored into RAM, random access memory. But the problem is RAM is that it's not really that good at randomly accessing memory. Let's look at the like motherboard of. So this is computer, like hardware. It's old image from Wikipedia. Anyway, so this is CPU, right? This is memory. So how a computer reads stuff from RAM? So CPU asks address, gets it, and then stores into the cache of near CPU. And when it tries to access some other thing, it first checks if there is stuff in cache. If there is, it just reads that. So it don't need to navigate from CPU to RAM a lot. If you take a look at this table, so CPUs are really fast. So to do one command, it takes like 0. something nanoseconds, and it's like 6 years old information. And then there is like cache, memory cache nearby or inside CPU. So it's level 1 cache, level 2 cache, and level 3 cache. I will not go into details, but accessing memory from those is pretty fast as well. Accessing data from main memory is quite slow. It's like 10 times, and compared to level 1 access, several hundred times slower, which is really bad. So what you want is to access from cache, which somewhere right here, and not from here. One of the reasons is speed of light. So traveling from here to here, there is like distance, which means you are limited by speed of light. And if you're accessing here, the distance is much shorter and it takes much less time. So let's go back to the plan because I forgot what I was supposed to speak. Okay, so that's why there's these three generic rules of how to manage memory and write fast programs. So how to do that in Python? You can't, because Python manages memory for you. Python is a language with garbage collector. So that's why it's on language to manage memory and not on programmer. It has a lot of advantages. You will not like have stack overflows and accessing wrong memory, but it means that it's much slower than managing memory yourself. So let's see how you would manage memory in Python. So main equals. So let's say I want to store 3 integers into array. It's going to be really small integers. It's going to be 1 byte size integers. So pointer, I have pointer, and I will ask I will ask 3 bytes of memory, and then I can just store things. Oh, and don't forget the free memory. So this is how you would ask for memory in C. It's very simple. You're saying, oh, give me the chunk of memory the size of this. That's it. So what it does inside the memory, it just like takes this 1 byte, 1 byte, 1 byte, and stores 1, 10, and 100. Sorry about my drawing skills. It's with a mouse and I'm horrible at drawing. So this is how, and that's it. This is like 3 bytes inside memory. No overhead, nothing. What would get, let's write like similar program in Python. So it would be called list, not array. So integers, let's say integers. So this is your main advantage of using Python. It's very simple to do stuff. You just write and it works. But let's make it like more similar to C version. So let's define main. Right, so, okay, sorry about my linter complaining about wrong program. So what happens here, like how Python does things. So everything in Python is a reference to PyObject pointer in C. So let's take a look at the C code for object. So it's line 105. So 105 is over here. So this is PyObject. It has 3. Actually, this is nothing. It's for debugging purposes. So usually it's empty. So you don't need to worry about that. And it has OB ref count. So as some of you may know, Python is a garbage collector, is a ref counter. So what it does, it increases at this point integer, it adds +1. So because you enter at the place where you need like new variable integers, it adds +1 to OB ref count. And at this point, when exiting function, it sees that you no longer have access to integers variable. Therefore, ref counter can be reduced by 1. And then it checks if, ref counter is equal 0 and frees the memory using free or malloc. What's the problem with that? So let's take a look at how integers are stored as well. So let's go into the plan. So integer is here, is defined here. So this varchar is just this object. So what kind of trick Python does is to make sure that any built-in object type, for example, long time, which is long type, which is integer. Python 3 doesn't have integers as integers. Every integer is long. So that's why you don't see big L at the end of big integers, because there is no big integer. They just integer or long or big integer, just one type for all integers. Anyway, back to the code. So this portion. So as you can see, the first element is by object. So the head of any object is the same as by object. So long object has, well, sorry about that. So line this 86. So every object in Python, built-in object has same head as a Py object. Therefore, you can point your pointer and say it's Py object. Because, okay, let's try explain differently. So this is Py object pointer pointing into object that's only consists of these fields. This is PyLong object. And its first attribute is object base, which is the same as this one. And these are required for other stuff. So for example, all the numbers you see, it's stored in OB digit attribute of struct PyLong object. Because these are the same, you can always point same pointer. So let's go back to our sample C. So let's say you have Python object, Python long object, some integer, right? And its pointer. You can always say like, okay, it's actually just Python object. And because memory layout is the same, everything will just work. And this object, the simple object, we're gonna ignore rest of the stuff in attributes. So this is how Python interpreter achieves pseudo object orientedness in C code, because C does not support object oriented programming, because it just has structs, which is just packed memory objects. So let's say I have some struct, my struct, in full. So let's say I have this struct. So after compiler passes everything, in memory, this structure will gonna look like that. So 8 bytes for the first, and for the full, I mean, and 16 bytes for the bar. And this is gonna look it's gonna look into memory. So everything in Python at the end of like interpreter or inside interpreter is just PyObject pointers to the memory somewhere inside the RAM. The problem, let's go back to this example. The problem with that is that you have PyObject pointer integers into which points to the list of like 3 items. Each item is also PyObject pointer objects, and they point in some other memory places where the like number is stored. And actually it doesn't, it points to a pylong object and pylong object, which points to digit array and which actually stores numbers. So something like that. What's the problem with that? It's all over your memory. It's not in one place. So go back to this one. You are missing this, your cache misses. It happens on this level, and you need to go to this level with this cost all the time, because Python interpreter just can't provide you with the memory at the same place, because it always constantly creates new objects and releases them from memory, creates a little bit more releases again, because it's a garbage languages with garbage collector. That's why it's slow. It's one of the reasons why it's slow. By the way, same problem in Java, because they have garbage collector, and it creates objects in memory all over the place as well. So if you can't manage memory yourself, you're probably gonna have this cache miss problem a lot, unless your compiler or interpreter is really, really smart. Then you probably don't. Let's go to my plan of my talk. So, so Python about Arena. So I said a lot of bad things about Python memory management, but it isn't as bad as I said, because Python tries to do clever things to reduce that. One of them is arenas, the concept of arenas. It's a memory pool. So at the beginning, Python interpreter gonna ask operation system to give some chunks of memory, like memory pools, and all small objects gonna be created in those pools. And that memory is not released. So Python is managing that memory instead of operation system. So let's say you have a function and you have 10 to 20 variables inside the function. And if these variables are small enough, they all gonna live in same arena, which means that they are nearby in memory, which means cache misses, CPU cache misses are less likely, which means Python program is going to be a little bit faster thanks to that. Okay, so let's do a little bit live coding just to see how it works, how the Python and C layer communicates and works. So maybe it's going to be a little bit more clear what I was talking about for this whole talk. So, okay, well, I'm in the right direction. So I have one C file. It's a simple C extension file as possible. It does nothing. It just defines module name byte manipulation. And I have run. Run for now prints the structure of a byte manipulation model. So if I run make, it recompiles, and as you can see, there is nothing right now, just like standard stuff of module stuff. So let's define some top level function. Oh, not, I need static. P methods. Okay, we have Py method def, so let's do that. It's gonna be array. It's gonna be static array. I'm gonna define it in place. Let's take a look how it actually looks. Okay, it looks like that. So name is gonna be, let's say, update into 42. Gonna be a very stupid name, but it says what I'm planning it to do. So I'm planning to write a function that updates integer to 42. And as you know, in Python, integers are immutable objects, so you are not supposed to be able to update them. But since we are writing code in C, we can do whatever we want, because we can access memory, directly memory, and manipulate memory in place. So flag is gonna be math, which means this means that we're gonna pass variables to the function as arguments, not as keyword arguments, and we don't have any doc string for this. This function does not exist. So each function must accept 2 parameters. One is module itself, and the other is arguments passed for the function. It must return something. There is already global variable by none, so our function is not going to return anything. This is not used. Let's add it here. Also, this needs some ending flag. So either you need to pass number of items in array, or you need to somehow inform Python that that this array is over. And so we are using similar technique as zero terminated strings, we're just gonna have everything be zero, and Python will know that this is the last element, this is the last element, and this is just zero flag to end array. So right, so we have methods, and let's try to recompile and run. Okay, we already have this method, this function in our module, byte manipulation. So let's try to call it. Okay, did I just get, yeah, I just get auto completion, I don't know. Okay, nice. And let's see. Hello from C. As you can see, let's run again. Hello from C. So it works. We're in C code and we're getting called from Python. Enum. Let's pass it here. And let's print. Right. So for now it prints 666. Prints 666. I want it to print 42. So let's try to do that. Let's try to do it in proper way, and then in really bad way. So the beginning of, so since I passed meth args as our flags for this method, args is just tuple. So I know that it's tuple, so I can actually ask size of tuple. I think its types is this num args. If we're gonna only accept one argument, and if it's not, we're gonna raise an error. Set string, yeah, this one. Attribute is going to be attribute error, if I'm not mistaken, and supports only one arg. So if I try to pass two args, let's see what's gonna happen. Nothing gonna happen because it needs to be negation instead of, yeah, so it actually throws an error. So this is how you throw Boolean exception in C. You just call PyError set string and pass the exception type and error message. So let's go back to normal. So at this point, we already know that args contains only one element, and we can try to grab it. Get item. Get item, and okay, I think it's like that, and it returns by object. Obj. Let me double check documentation. Of this. Okay, somehow it throws me into old one. So get item. Oh, it returns borrowed reference, which means that I got the object and now I'm responsible for that object. So I should increase ref counter myself and decrease it when I don't need that object. So incref obj and decref. Okay, so we are safe. We are not going to corrupt memory. and we can see what it has. So it has a ref count and object type. We only care about integers and type. Okay, I think it's, yeah, this one. We cannot compare pointer. Okay. So if object type is not integer, I'm gonna throw error again. I'm gonna throw this time type error. Supports only ints. Oh, I removed this. Also, we are exiting, so we need to decrease reference for the object. So at this point, we know that it is integer, and as I said, integers are stored as long objects, and we can actually cast pointer to long object. Oh. So we have long object, but what I want to also limit, I don't want to work with really large integers. So if I have really large integer, it's gonna be stored in really complex way, and I don't want to deal with that. There is a way to find size of object. So can I pass long object? Yes. P. I'm gonna get size of this object. So let's go back and look at this. So this is, oh, this is the implementation. So every integer is array of integers, and if its actual value is calculated using this pseudocode, so going through each element and multiplying by 2 raised by some large number, which is really hard to calculate, and it looks like nonsense if you go over more than one array item. If it's just one, so if you're gonna rise 2 by 0, it's gonna be equal 1, so it's the same number. That's why I'm limiting everything to one number. So if size is 1, sorry, not 1, I'm gonna say, well, error suppose only small ints. Let's see, supports only small ints because size is too large. Oh, I'm gonna change that to small again. Oh, there's also one important trick or hack Python does. So if I'm gonna add minus sign here, actually it fails with value error that it only supports small integers because size is negative now. So it's a hack. All negative numbers have negative size. I can prove that actually with LD and size. So size is -1, which is nonsense. Size cannot be below 0, but this is the hack for Python to store negative integers. So let's also double check size. No equals. Now it's fine, right? So at this point, this is a very good point. Now I know that our object is small integer and nothing else has been passed. So now it's safe to start hacking on it. And it's not gonna be very complicated. I'm just gonna enter anything I want into this array where the number actually is stored and put on the memory. So I'm gonna just assign 42 and that's it. Yeah, it prints 42. If I just run, yeah, 42. If I change to, I don't know, 1, 2, 3, right? It's still. The thing is, it seems innocent to just assign number, but since integers in Python are supposed to be immutable, and I'm working with them as they are mutable, I'm destroying everything that's in Python interpreter. Because let's see, like I can change, I don't even need variable. I can just pass 666 here. And if I print 666 here, it changes to 42. I change the meaning of 666 in Python interpreter. It's no longer, it doesn't make sense anymore. Same. And I can actually like, okay, I change 1 to 42. It seems like, oh, it's a cool thing to do, but I do remember actually getting, yeah, segmentation foul. So I break Python. Why? Because it probably uses number 2 somewhere else to access memory, and it assumes that it's true, but I changed it to 42, so maybe it asks to operation system to remove stuff, and it tries to remove from different process or different program and says, no, you cannot do that. It's segmentation fault. So, and what else? And I played around with that yesterday, and there is a trick how to actually get Python to print 666 even if I updated 666. So if I go like call integer around, oh, not like that. I need to actually start using float number. So if I use float number, probably like turning float into integer doesn't use some optimization that interpreter does if it sees two 666 in the same file. So it's cool, but it doesn't work if I have something like that. Whoa. Why? I'm missing. So if I have something like that, it doesn't work. Why? There's this again memory management trick Python does. So first, I think 250 numbers. So 1, 2, 3, 4, blah 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 250 is actually created when interpreter starts. So they always exist to speed up the process, because you're probably gonna need only small integers in your program. So they never create them, they just reuse them. And I have changed it that very important number that all other Python code is going to rely. So it's very dangerous thing. It's really bad code I've written and showed you how to shoot your leg but it's fun. So I'm gonna end my talk with that. Thank you everyone for listening and watching me write that funny but stupid code.
All right, Patras, thank you so much. This was definitely not stupid. And I think your drawing skills are very good. I was able to understand everything. So yeah, thanks again, Patras, for this great presentation. And let's see if there's any questions from the attendees. We can do up to 10, 15 minutes, so 2-3 questions. So anybody, feel free to post some questions in the chat. And if not, I also want to ask everybody a question. Do we need a 10-minute break, or do you want to jump into the next presentation? All right, so I guess we'll keep going. That's what I can see right now, and we're still waiting for some questions. I will also mention one thing at the end, but I'll do it now as well. We do have a Discord channel, so if you will have any extra questions or you will come up with a question later on, after the meetup, you can just go to the Discord, which I will share after the both presentations. And there you can go to a live chat with the presenters, with the speakers, to ask any questions you like, and always feel free to use, Discord, as a way to use, to just communicate and discuss things. Oh, and we have the first question. It is from Sharunas. So we need a custom C module for optimized memory usage, question mark?
You kinda do, and you kinda using it without knowing. So a lot of important functions in Python, its interpreter or standard library are written in C. That's why it's fast, right? So like string manipulation and so on, it's fast because it's written in C. Plus, if you are using Python as a glue language, so you're usually using other programs or processes that are written in C. So if, for example, you're doing web development, you're probably using some database. So let's see, like SQLite written in C really fast, optimized, and then some web server, Unicore or something, also really fast. So what you care is about database speed and your web server speed. You're doing your business logic in Python, and you're like gluing these two important things together. But the speed at that point doesn't matter much as like expressivity and the easy to write your business logic or easy to understand your business logic. As you have seen, like writing C code is really verbose if you want to be correct.
All right, so thank you for the answer. Are there any more questions? I guess not. So if you have any more questions.
Sorry, I had muted. Just one question. Tadas, thanks for the talk. Very insightful. I just want to know, like, how often can we expect to face this need to do this kind of optimization, or you had experience where you needed to write some of these things in similar code in your, I don't know, professional life?
None. I don't know. Probably if you are doing something and you see the need for, plus there's other tools like Python. You can do stuff in Rust, you can do stuff in Go, or you can just use like all these microservices approach. So you just write another thing that runs on different process and you communicate between processes, one written in Python, other in whatever language you want. So you probably don't need that unless you want, or you are working on some specific problem. The rest of the world is not working. So it's more like understanding the car you're driving than, oh, I'm gonna need that in my professional life thing for me.
Okay, thanks.
All right, so I see one more question, so we can do one more question and we'll continue to the lightning talk. Is it any best practices for using memory optimization, maybe any programming patterns?
So as I said, like as less memory allocations as possible, as less freeing memory as possible, and put things together that are gonna be accessed by CPU together. So if you're gonna use some array, if you're gonna go through some objects in a for cycle or while cycle, and you're gonna access them one by one, put them into nearby location in memory. So that's the gist of it. And patterns, I think it's too low level detail for the patterns. But in Python, let's say you have a 2D array of things. So access them the way they are stored. So if they are stored starting from x-axis to y-axis, so for each first like y-axis then x-axis, so they're gonna be accessed at same order as they store in the memory. But there's no like object-oriented design patterns or how to manage memory.
All right, so I guess, thank you, Sharunas, for great questions, by the way. Now that we have finished the Q&A session for the first presentation, let's get started with our today's lightning talk. So Albertas, feel free to start, and yeah.
Hello. So, today I'm going to talk about testing and how basically how do we do tests in Python. And the talk is, I guess it's a bit longer than a lightning talk, but we have time, right? And it's kind of, I guess it's pretty basic, geared at beginners, but it's also two-pronged. There's like the first part is more like philosophy. So what's the problem? Why is testing hard? Recently, I've come across this tweet by a famous Agile coach. I believe he's one of the signers of Agile Manifesto, about testing. And if you're interested, I recommend that you look it up and read it. I'll post the link to my slides into the chat and on the Facebook event, so you can do that later. So what does he say? Essentially, he says, in the 70s, there was this approach or method of testing called black box testing, which is elegant on the ideal level. You consider your system as a black box with some knobs on the front, and you basically click the knobs and see what comes out without considering what's going on inside. So you just provide inputs and check outputs. And in the 70s, it was probably pretty a sensible strategy. The computers were small, like several kilobytes, I don't know, tens or hundreds kilobytes of memory. And it was possible to make tests that completely tests the systems of the day in the black box fashion. But combinatorics is in play here, and nowadays it's much harder. Consider this: if we have a function that has 5 arguments which are Booleans, there are 32 combinations of arguments, so you can just write 32 tests and completely cover what the function can do. But if you add another parameter, which is also a Boolean, your test suite grows by a factor of 2. But what we have to do, or what we can do, is look inside the function and see that actually a is an independent variable. It does not interplay. What it does not influence how other parameters are handled and what they do, and we can kind of separate it into into a separate test. So we can have a test where a is true or false, and then have 16 combinations of the other arguments. And what we've come up with is a gray box test, which is sort of like a black box test. We're still twiddling knobs on the black box, but we have some insight into what's going on in the internal structure of the system we're testing. Modern systems, of course, with the web, with asynchronous kind of universe, and the code sizes of code bases, it's just impossible to do a full black box test of any reasonably complex application. For example, if you have a web page with 10 fields and you test 3 values for each of them, the full black box test is 60,000 test cases. So we have to be smart. We have to think about what's actually going on and do trade-offs. And our tests are always incomplete and fragile, but still we have to make do and try to optimize what we have. Now, the practical part of the talk. In Python, tests come in 3 flavors, or you could make more, but generally there are unit tests, which are small tests testing individual classes, objects, or functions on their own. There are integration tests that are testing a larger aggregation of modules, objects, maybe bringing up the framework with the configuration. And then there are end-to-end tests where the system is tested in this black box fashion through its inputs and outputs, like through driving a web browser and checking what's coming up on the screen. So let's look at the examples. Here's a simple unit test. So well, here we're imagining we have some small web application which can be written in any framework. My examples, it's Pyramid, and here you can see it in the models. The user is an SQL Alchemy model. So we're creating a user and we're checking that the dunder JSON dunder method creates a JSON representation with object. Simple, self-contained, no external effects. This is kind of the sweet spot, and these tests are really fast. You could run, I don't know, hundreds of such tests in a second. If you have some some external dependencies, some library, network communication, some other systems that need to be brought up. What you do in unit tests is you stop them or mock them out. And mock or unit test.mock now in the standard library is a library that helps you do that. For example, here we have some method that sends an email and does that by calling the smtplib.smtp to create an SMTP connection. So what we're doing is we're patching it with mock, and basically we're creating a mock object that has a sendMail, which is a mock that can be called and returns this value when called, and we're just calling it, and then we're testing that the smtplib.smtp was called with these arguments, and then that the smtp.sendMail was called with these arguments. So this is also a fast, self-contained, isolated test that tests one function. But the risk with these tests is that when something changes, for example, the API of a library changes or some other conditions outside of our control, then this test will still work, but the code will be broken. One particular example of this was when migrating code from Python 2 to Python 3. People who had really good coverage, but with these mocked out isolated tests, could not really depend on the test suite to tell them if their code still works on Python 3, because a lot of standard library libraries and functions got just reshuffled and changed in some ways. And you needed to have tests that actually exercise them, import them to check out whether your code still works or not. So this is what we have with the unit tests. We need to test in more integration. And here's an example. For integration tests, we need to assemble these systems, bring stuff up, and we need to do some setup. And with PyTest, what you can do is have fixtures for your tests. And here's an example how a fixture bringing up an SQL Alchemy session for Pyramid looks like. So we're creating an SQLite engine, we're configuring, binding to it, and then we're creating an admin user so that there's like a user in the database. And that's it. Then on this yield point, it's fed to the test, and then it's cleaned up. We need to bring up our framework pyramid as well, and you do it by using the testing setup function call also in the PyTest fixture. And then in the test, you're just providing these, declaring these arguments that tells PyTest that you need the DB session and the config fixtures from your conf.test.py file. And you just get these configured objects. You have the database ready and working and pyramid configured, and you can create a view and call it and check that the response is what you expected, and that actually here we're kind of mocking the cookie setting method of the security policy. We're checking that the cookie was set, so the kind of the authentication went successfully. Now, with these integration tests, also there are some risks that our integrations are testing some modules also in an environment that is not that realistic. So if our routes are misconfigured, or if the front end and back end code does not agree on the format of these JSON messages being sent around, we need something more: integration tests, or I mean functional tests, or acceptance tests, or end-to-end tests. So these are different names for the same thing, essentially. End-to-end is like a technological kind of moniker, because we're using a web application from the browser, end-to-end. Functional tests, because we're using the whole system functionally. And acceptance tests, because in some agile processes, these tests are provided by the user and are considered as acceptance criteria. Does the system do what the user wanted it to do? So how do we go about setting them up? Well, you just install the plugins for PyTests, that PyTest Pyramid Server and PyTest Splinter. Splinter is a wrapper for Selenium and other kind of browser testing things that provides a high-level API. And you're getting Chrome driver to be able to run your tests with a real Chrome engine, either a real Chrome browser where you see how things are happening, or with a headless version where it's just happening and all you're getting is just errors or screenshots. Now, for this PyTest Pyramid Server, you need to provide a testing ini, which is like usually you have an ini file for your pyramid application. So you're providing a different config for your application, which is used for the testing environment. And you see database and so on. Then with these fixtures, basically having installed these packages, you have the browser, session browser, and pyramid server fixtures hooked up. And when you require them, you get a server started and the browser fired up, and then you can just visit the server's URI with the browser, and then you can just wait for texts, click on buttons, fill functions, fill form fields, click, and so on. Now, if you want to see what's actually happening, you have to do this in PyTest ini. You have to, or you can provide command line arguments to PyTest, or just add them to your config file that you want Splinter WebDriver to use Chrome. Then instead of headless Chrome, then the browser will pop up and you will see your tests running. Now, these are the three kinds of tests, basically what I wanted to talk about. And all of them have pros and cons. Unit tests, you can really get into all of the branches and test all the cases in minute detail, have high code coverage, but you have to keep in mind that unit tests don't have these drawbacks. They can still pass when the assumptions your code is making are wrong. So you need to have integration tests and end-to-end functional tests as well. And as I said, unit tests are fast. They're like 10 tests in a second or so. Then integration tests with Pyramid, I think it's starting and bringing down the app for each test. So it's, I don't know, a second per test or so. And the browser tests, basically each of these lines is on a magnitude of a second. It can be like 3 lines per second or so, but you can see just things happening in the browser. These texts are entered by sending the browser key press events, so it just cannot be fast. So this test would take, I don't know, 30 seconds, maybe a minute. But you still need all these kinds of tests in order to be reasonably confident that everything's working. And that's it. Any questions?
Thank you, Albertus, for this presentation. Yes, and feel free to ask any questions.
I can start. I have a question, like what percentage of time you spend for writing your tests, and like you had a long career, did it change? Maybe you started without writing tests or started like spending 50% of time writing tests and it changed over time. Like what was the progress of your time that you invest into writing tests?
I don't know. I don't think it changed much. Well, I got lucky that the first job where I was programming Python, our employer also pointed us to extreme programming, had all the books about extreme programming, which is one of the early agile methodologies. And basically he insisted that we do test-driven development all the time. That's how I started. Basically all my professional Python code is test-driven. And as you know, tests are a significant part. After you figure out how to solve your problems, basically tests take not that much, but still they are good. Tests are usually more verbose than the code they're testing by a factor of 2 or 3.
Okay, thanks.
We have a question from Sharunas. He's being super active today. Thanks, Sharunas. What modules is better for microservice testing, for example, between two systems and microservice in between?
Oof. I don't know. There is this Python library called VCR, which lets you record responses of an HTTP, basically a HTTP session, and to play them back to make sure that your single system or your single service that's using other services over HTTP APIs is working. But still, I don't know. It's how would you go about doing or rigging an end-to-end test for a system of 3 services? You tell me, how do you do it?
Could you, there's another question. Could you recommend some worth reading literature about test-driven development?
Sure. So there is a good book called Test-Driven Development by Example by Robert T. Martin. It's like 20 years old or so. And its preprint is available, it's by Kent Beck. Its preprint is available on the web. You just Google test-driven development by example PDF and you find the preprint.
All right. Thanks for the question.
So
and thank you for the answer.
definitely recommend that book.
Great. Any more questions? Oh, I see Albert has posted a link to the book. All right, so I guess I'm not going to be waiting for any more questions. And before we finish, I wanted to share a Discord channel with you. Albert has already sent a link to it, but I will do it again. where you can submit all of your questions, discuss different topics, and just talk about anything you want related to Python. There will be two channels for each of the speakers where you can have live conversations with them. So I'm going to share my screen quickly so you can see how Discord operates if none of you have used it before. Just give me a second. So let me know if you see my screen.
Yep.
All right, great. So here's the main page of the channel. It's a fresh channel, so you know, the more activity there is, the better. And there are some general text channels where, you know, general, help, web, data, and then we have two web voice channels where Albertas is already in one, and there's another one for C Python. So yes, this channel is, you know, for Python lovers, and you can just, you know, we're trying to build a community here as well. So, you know, it would be great if you could be active on it. Definitely we'll be waiting for questions, thoughts, discussions, you know, anything goes. All right. For now, that's it. Thanks everyone for attending this meetup. And of course, we will keep you posted when the next one will happen. And see you on Discord, and stay safe, guys.
Thank you.
Thanks, everyone.
Thanks, bye.